Chapter 2, Section 4, Graphing Polynomial Functions. Before we start graphing our polynomial functions, we would like to discuss something called the end behavior of polynomial functions. The end behavior of a polynomial function is describing how the graph of a polynomial eventually behaves. And it's all dependent upon the leading term. Now to determine the end behavior of a graph, all we have to do is look at the leading term. Now let me give you how the end behavior is described according to the leading term. So watch this. If the polynomial function has even degree, so if it's degree 2, degree 4, degree 6, and so forth, with a positive leading coefficient, that means the graph eventually behaves like this. That means eventually the graph goes up forever on the left, and it goes up forever eventually on the right. Now there might be some things that happen in between the graph, in between these two branches. There's some intercepts and things like that, but eventually the graph goes up forever on the left, forever on the right. Let me give you proper mathematical notation for this end behavior. This says as x approaches, that arrow means approaches, as x approaches negative infinity, that means your x values are getting smaller and smaller and smaller. F of x approaches positive infinity. So as you go to the left, right, because when x values get small, that means you're going to the left. So as you go to the left, eventually your y values keep on getting higher, larger and larger and larger to positive infinity. So this notation describes this end behavior. As x values get infinitely large, this says as x approaches infinity, that means x values are getting larger. When x values get larger, that means you're moving to the right. This says f of x, or y values, are also getting infinitely large. F of x approaches infinity, so that means it's going up forever. This notation is the mathematical notation for this end behavior. The next case is when the function is even degree but with a negative leading coefficient. If the leading coefficient is negative, then the end behavior is like this, where it's down on both sides. Remember, there's a lot of stuff going on in the middle, maybe some intercepts and things like that, but eventually the graph goes down forever on both sides. Here's the mathematical notation for that. So we write as x approaches negative infinity, that means as you let your x values get smaller and smaller and smaller forever to the left, the graph goes, f of x approaches negative infinity. Okay, and then as x approaches positive infinity, so as x values get larger and larger, your f of x values approach negative infinity. All right, let's go to the next case. Now we go to where the degree of the function is odd with the positive leading coefficient. The end behavior is up forever on the right and then down forever on the left. Once again, there's things happening in the middle, right? Intercepts and so forth. The mathematical notation is as follows. As x values get infinitely small, so as x values approach negative infinity, f of x approaches negative infinity. As x values approach positive infinity, f of x approaches positive infinity. Okay? So this here says as you go to the left forever, the graph goes down forever. As you go toward the right, the graph will eventually go up forever. All right, case 4 is the last case. This last case is also odd degree, but a negative leading coefficient, and that would give you this end behavior in your graph. And one last time, there's a lot of things happening in the middle, some intercepts and things like that. Here's the mathematical notation for the following. As x values approach negative infinity, f of x approaches positive infinity. As x values approach positive infinity, f of x approaches negative infinity. In words, this would say, as your x values get smaller and smaller and smaller, the graph will eventually go up forever. As your x values get larger and larger and larger, your graph eventually goes down forever. Before we actually graph a polynomial function, I want to walk you through the steps that we are going to follow for graphing. The first is we're going to determine the end behavior. Then we'll find the intercepts, the y-intercept and the x-intercepts, also known as the zeros of the function. And then all of our polynomial functions will have a graph that is a smooth curve. That's very important. All right, here we go. Here comes our first example. Let's graph this degree 4 polynomial function. So it's a quartic polynomial function. All right, first things first, end behavior. Notice that the degree is even, and it's a negative leading coefficient. That would be case number 2, and the end behavior we know will be down forever on both sides. I can also write that in words if you'd like. So I can say as x approaches negative infinity, or I guess negative infinity first. Negative infinity, then f of x approaches negative infinity. Also, as x approaches positive infinity, f of x approaches negative infinity. All right, so this is the end behavior. Basically, this math notation here just says that the graph is going down on both sides. Okay, next thing, let's find the y-intercept. Now don't forget that whenever you find a y-intercept, you let x be 0. So then we're going to substitute 0 in for all x's. In other words, we're going to evaluate f of 0. Now I want you to see something. If you let all your x's be 0, then this term is gone, this term is gone, this term is gone, this term is gone, and the only thing that will remain is 45. So therefore, 45 is your y-intercept. All right, so I'm just going to write f of 0 is equal to 45. So your y-intercept is 0, comma, 45. And that will always be the case, everybody. When your function is written like this, where it's not factored at all, then the constant term is always your y-intercept. All right, so you may want to add that to your notes. All right, let's find the x-intercepts, which are the same thing as 0. Let's find the zeros of the function. Now, let's get started by using the rational zeros theorem to get a list of possible rational zeros. So remember the rational zeros theorem, it tells you P over Q, right? So it'll be factors of 45 over factors of -1. It'll give you plus or minus all of these factors. All right, the first thing I'm going to do is I'm going to use synthetic division to see if 1 is a 0 for my function. That is to say, I'm going to check to see if 1 is an x-intercept. All right, synthetic division shows me that 1 is a 0 or an x-intercept of the graph, so this is really great news. Now let us not forget that you started out with something degree 4. Therefore, this is now degree 3. Okay? Now, before I go and choose a different value from this list and continue with synthetic division, I want you to notice that all of the signs are the same. There are no sign changes in this new depressed or reduced polynomial. No sign changes. That means that there will be no positive zeros no positive zeros for this reduced polynomial. So I'm not going to check 3 next. I'm not going to check any positive possibilities. I'll only check negative possibilities. All right, let's try -3. Let's see if that works. Also, keep in mind that I'm using these coefficients now, right? I'm not using the original. I'm using the quotient here. All right, let's try this. Move this up for us a little bit. So let's check. We can see through synthetic division that -3 is also a 0. So this is very good news. So far we have 2 zeros, or 2 x-intercepts, 1 and -3. And then notice that now we've hit degree 2. So since I have degree 2 now, I will no longer do synthetic division. Instead, I will write this as -x² minus 8x minus 15. I'll set this equal to 0, and I will solve this by factoring. When I factor out a negative, I get x² plus 8x plus 15 is equal to 0. Remember that if something doesn't factor for you, that's okay. Just use the quadratic formula. All right, so this factors as follows here. And then what you would do is set each variable factor equal to 0 and solve. You can disregard that negative that's out front. So then the other zeros are -5 and -3. All right, I want you to notice something. -3 showed up here, and it also showed up here. So -3 showed up twice. That means -3 has multiplicity 2. So let's write this down. All right, everybody, these are the x-intercepts that we just found, and we just saw that -3, 0, that x-intercept, or that 0, showed up twice, so it has multiplicity 2. This has multiplicity 1, and this has multiplicity 1. Now listen carefully. Now, if a 0 has odd multiplicity, odd meaning multiplicity 1, multiplicity 3, multiplicity 5, and so forth, the graph will go through that x-intercept. But if a 0 has even multiplicity, that means multiplicity 2, multiplicity 4, multiplicity 6, and so forth, the graph will bounce off of the x-intercept, which means the graph will not go through the x-axis at that value. I'll show you exactly what we mean in just a minute. So you can see that because this 0 or this x-intercept has even multiplicity, it'll be a bounce point, whereas these two x-intercepts have odd multiplicity, so the graph will go through these two x-intercepts. So these two, the graph will go through them, but here the graph will not go through that point. All right, let us show on a graph what we have so far in a Cartesian plane. All right, the first thing I will do is I'll plot my x-intercepts. So one of them is 1, 0, another one is -3, 0, and then -5, 0. My y-intercept is 0, 45. And then what I'll do is I'll use the end behavior to say that the graph goes down forever on both sides. Okay? Now remember which one is a bounce point? -3 is a bounce point. So when you get here, do not let the graph go through that point. So here we go. The graph goes through this x-intercept. It will come down, touch this one, and bounce right off of it. It'll go through the y-intercept, and then it'll go through my last 0 there. So this is the sketch of the graph. Okay, let's graph this brand new function. It's a cubic, degree 3, cubic polynomial function. First things first, let's get the end behavior. Notice that the degree is odd. Whenever the degree is odd, that means the end behavior will not match, right? One end will go up and the other one will go down. Okay, when that's true, whenever the degree is odd. So one end will go up, the other end will go down. Because the leading coefficient is positive, it will go up forever on the right, it'll go down forever on the left. All right, next, let's find the y-intercept. Now I hope you remember me saying that in order to find a y-intercept, you let x be 0. And that would mean this term goes away, this term goes away, this term goes away. The only thing left standing is your constant term. So 2 is your y-intercept. Mathematical notation for that would be g of 0 is 2. So the y-intercept is 0, 2. Now for x-intercepts, or the zeros of the function, we're going to use the rational zeros theorem to get a list of possible rational zeros. And that leads us to these 6 options. Positive 1, negative 1, positive 2, negative 2, positive 1/2, negative 1/2. All right, now we're going to use synthetic division and see if you and I can find a 0, an x-intercept. After some searching, I found a 0. I tried -1 first, and it works. So now, not only is -1 a 0, but also we started with degree 3, so then that means this is degree 2, which is a quadratic, which means I can stop looking for zeros using synthetic division, and I can just factor, hopefully, or use a quadratic formula to find the last 2 zeros. I notice that this factors like that, and what I can do is set each factor now equal to 0 and solve, leaving me with x is equal to 2. And here, after adding 1 and dividing by 2, you get 1/2. All right, so we have all 3 zeros. So the x-intercepts are -1, 0. That's the first x-intercept we found. 1/2, 0, and 2, 0. Now all of these x-intercepts appeared or showed up just one time only as solutions to the polynomial. So they all have multiplicity 1, which is odd multiplicity, so the graph will go through these points. So none of them are bounce points. All right, let's get the curve going, the graph. All right, the first thing I will do is plot the x-intercepts, and they are 2, 0, 1/2, 0, and -1, 0. And don't forget your y-intercept of 0, 2. Also, don't forget your end behavior, which says that it's going up forever on the right and then down forever on the left. Now, remember that each of these x-intercepts have odd multiplicity, right? So your graph will go through these points. None of them are bounce points. So through that x-intercept, through the y-intercept, through that x-intercept, and through that x-intercept. So there's the final picture. All right, next example, graph this polynomial function. All right, here we go. First things first, end behavior. Now this one's interesting because the function is already factored. It's factored for you. You can't really see what the leading term is. And you need the leading term in order to figure out the end behavior. So what I'm going to do is I'm going to take every leading term from each factor. So 2 times x squared times 4x. multiply all of them together to get the leading term. Let me make sure you caught that. 2 is the leading coefficient there. This is x right there, times x squared. Be careful to grab that x squared right here, and then 4x. And when you multiply all this together, you get 8x to the 4th power. So you can see that your degree is even. Once you have an even degree, you know the end behavior will match, either up on both ends or down on both ends. Because the leading coefficient is positive, I know it'll be up on both ends. So the end behavior is up on both sides. All right, let's go to the y-intercept. Now, finding the y-intercept, I wrote it down wrong over here, guys. Hold on. Finding the y-intercept has been relatively easy. All we've been saying is the constant term is your y-intercept, right? However, in this example, because it's factored already, finding the y-intercept is going to be just slightly more challenging. Remember what you have to do. You have to plug in 0 for x. So f of 0. You're going to actually have to do the arithmetic here to find the y-intercept. So notice I'm plugging in 0 for all of my x's, okay? 0 plus 1, quantity squared, and then 4 times 0, and then minus 1. This will give me 2 times negative 3 times positive 1 squared, which is just 1, times negative 1. So then this whole thing will be 6, positive 6. So the y-intercept is 0, 6. That was a little bit more involved than the previous examples, and so was the end behavior. But when I find x-intercepts, look how great this is, you guys. Because this is already factored, all I have to do in order to find the x-intercepts is take each factor, set them each equal to 0, and solve. I don't need the rational zeros theorem. I don't need Descartes' rule of signs or anything like that. All I do is take each factor, set each of them equal to 0, and solve. That'll give me my x-intercepts. So when a function is factored, it's easy to find the x-intercepts. All right, one of the factors was x minus 3, so I'll set that equal to 0. And the other one was x plus 1, quantity squared, set that equal to 0. And then I have 4x minus 1, set that equal to 0. Okay, I don't want us to lose something very important. This factor right here is going to give me a 0 of multiplicity 2. Let me show you how I know that. When you go back to the problem, there we go, look at this factor. Look at the degree that's on the factor. X plus 1 quantity squared. That means you'll have 2 copies of that x-intercept. 2 copies. When I go to set the factor equal to 0, of course I only take 1 copy. But don't forget the power that was on that factor. It was 2. So really this will have multiplicity 2. So each of my x-intercepts are 3, negative 1, and 1/4. This x-intercept here is multiplicity 2. So this one is a bounce point. Okay, I'm just going to write bounce point. Okay. This one here is multiplicity 1, and this is multiplicity 1. So be very careful that you grab the multiplicity. All right, let's go to graph the function. All right, I'm going to plot my my x-intercepts. One of them is 3, another one is negative 1, and another one is 1/4. The y-intercept is 0, 6, okay? And let's not forget which of these x-intercepts is the bounce point. X equal to negative 1 is the bounce point. So when you get here, make sure you just bounce right off of that point. Let's also not forget the end behavior. The end behavior of the graph looks like this. Up forever on both ends. Now, here we go, bounce point, so don't go through, and then through the y-intercept, through 1/4, and then through 3. All right, this is the one and only, sorry, hold on. There we go. This is the one and only bounce point. All right, there's your graph. All right, this will be our last example. First things first, let us graph, or let us determine rather, the end behavior. Now, because this function is already factored, I'm going to take each leading term from each factor and multiply. Make sure you understand this is x squared, multiplying that by another x squared, be careful, x squared, and then an x. When I multiply all this together, I get x to the 5th. Notice that the degree is odd. That means the end behavior will not match, right? It'll be different. Up on one side, down on the other. Notice that the leading coefficient is positive 1. Therefore, it'll be up forever on the right, but down forever on the left. Okay, let's find the y-intercept. In order to find the y-intercept, we're going to plug in 0 for x. So here we go, 0 squared times 0 plus 3 quantity squared times 0 minus 4. Do you see that you're going to get 0? Because I don't even care what this turns out to be over here. 0 times anything is 0, so this is 0, 0. 0, 0, or the origin, is the y-intercept. Now, to find the x-intercepts, or the zeros, of the function, we will take each factor and set it equal to 0. Now, x minus 4 is a factor. Notice that its power is 1. That means this will be multiplicity 1. X plus 3 is a factor. I'll set that factor also equal to 0. But notice that its power is 2. That means this will give me a 0 of multiplicity 2. X is also a factor. I'll set that equal to 0. And that'll be x equals 0, right? But that will be a 0 of multiplicity 2. All right, everybody, these are the 3 factors that I mentioned. One of them was x squared. I just took 1 copy. Another one was x plus 3 quantity squared. I just took 1 copy. And then the last one was x minus 4. So then your 3 x-intercepts are 4. This one is already at 0. And the third one, -3. Now, do you remember that this factor was being squared? Do you also remember that this factor was being squared? That means each of them will have multiplicity 2. Multiplicity 2. This one is just multiplicity 1. So this is a bounce point. I'm just going to write the word bounce. And so is this one. This one's also a bounce point. The graph will go through this x-intercept. All right, let's show all of this in the plane. All right, don't forget that your intercepts, your y-intercept was 0, 0, and that's also your x-intercept, by the way, -3 and +4. Again, I want to repeat myself. Whenever your graph goes through the origin, then that point is both an x-intercept and a y-intercept. Let's not forget our end behavior. I'm going to scroll up on the screen so you can be reminded of your end behavior. Up forever on the right, down forever on the left. So I will be going up forever this way, and then down forever on the left. Okay? Now, don't forget also which of your x-intercepts are bounce points. So the origin, x equal to 0, right there, that's a bounce point, and so is -3. This is a bounce point. So, with that being said, I will not cross there, I'll just bounce, and then this is a bounce point, and then finally I can cross that x-intercept. So there's the final picture. All right, everybody, that wraps up this lesson for graphing polynomial functions. I hope you learned a lot. I love this section because it takes a lot of what you and I were discussing in earlier sections, and you can actually see it all come out, come into fruition. You can see it all come into play here. Multiplicities of zeros and intercepts and behavior, it's all here. All right, everybody, I'll catch you in the next lesson, which would be 2.5. Catch you later.